So it took me a long time to get it right because I had calculated the group time average treatment on the treated incorrectly. So I kept getting the wrong answer. In fact, I was always getting the right answer. So we were looking for the group time average treatment on the treated for the 1998 group, which means I've got to use this treatment effect here, 6. Doing it for 2000. That's going to be 6 times 2000 minus 98 plus 1. Should be an 18. Okay, so let me drop PG3, 2000, ATT, so 2W0, ATT. Okay, so I'm going to drop those. All right, so let's go down here. Where is it? Here. So here's the form, right? Logit the outcome of the year of the treatment and it being in the group or it being in the control. Yeah, Andre, I know. Yeah, same here. I kept getting 18. I was like, it's supposed to be 12. And, you know, this, I'll have you guys know, I currently have a student. I think I told y'all this. He is working with me and Pedro to write up the the Callaway and Santana estimator, as well as this double robust diff and diff estimator that Pedro has also developed into a single stata package called DID. There's already one in R called DID, so we'll be doing one in stata. So this summer, we're working on the package. Right now, this is all I have, but I'm going to show you another do package, do file that I'm going to at least put in the, well, actually, I'm going to show you where to download it on GitHub yourself. But yeah, you can see here, Andrea, right, and everybody, how tedious this is, right? So imagine you had to make all those group time average treatment on the treated and then add them up together manually. It would just, it's just like so easy to make mistakes. It took me so long to get this right. And I only knew I was getting it wrong because I knew the underlying thing. So the programming that's required is like high school 9th grade level, but it's so easy to still make these mistakes, okay? So, so here's the form. Whatever your group is, mine's G3, whatever the year of treatment is for that, so that's 1998, for the treatment group, that's G3, or anybody who's left over that isn't yet treated, which is G4. And then I had to, once I did that, I had to get my logit and my predictions. And I'm just being extra cautious because I was having trouble getting the right answer the whole time. And I kept thinking, oh, it's because I'm doing something with I've got too many, I don't have enough missing values, but that wasn't actually it. I just was getting, I didn't know what my parameter was. So then you get the post period 2000, get the pre-treatment period 97, get your weights, get your, your numerator, get your total weights, numerator divided by denominators, get all of your long difference elements for the treatment and control, and run it. 18015, 18.0159. Okay, so let's look at that. DI, 4 times 2000 minus 19.8 plus 1. Nope, sorry. DI, 6 times 2000 minus 19.8 plus 1, 18. Okay, now that we have done a billion of these, question. How do we calculate the group time average treatment on the treated for the 4th group? Anybody want to guess? Can we do it? With this universal adoption, staggered rollout where everybody gets treated, is it possible to calculate the group time average treatment on the treated for the 4th group? For instance, right? Let's look at this. We know what those parameters need to be, right? For group 4, treatment effect is a 4. So let's say we wanted to get tab treatment date if G4. All right, gets treated in 04. So say I wanted to get the 2008 it's a 20, right? If I wanted to get the group time average treatment on the treated for the fourth group in 08, it is a 20. How do I go about estimating it? Because look, get down here, all right? You got to take that form right there. Okay, so we got to get this form, all right? So let's do it real quick. Logit G4 if year equal 2004 and G4 equal 1 or time till less than 0. G4, 2004. Huh, it didn't run. Even though that does run. So if I do G2, it runs. But if I do G4, it doesn't run. Does anybody want to take a guess as to what's going on? Why is it not running? Why can't I run that regression? Actually, look. Let's look at it. Okay, load G4. Summarize group if year equal 2004. All right, tab group. Oh yeah, so I go tab group. No, that's not what I mean. Let's see. I want to see. I got somebody that's got a comment here. Francesco, because there are no longer any untreated. Exactly. For staggered adoption in diff and diffs using the Callaway and Santana estimator, it is never possible with a complete universal coverage, a staggered rollout where every unit is eventually treated. It is never possible to get all group time average treatment on the treated because you have to have a never treated or a not yet treated group as a control, and at G4 everybody's treated, right? Because look, tab time till if G4 equal 1, if year equal 2004. There are no, notice, look, if I want to do the time tills in year 2004, there are none. There are no negative values, right? We needed negative values here, and there are none. So we did 2004, there are no negative values. That was not the case earlier when we did the 2000. We had some negatives. We had some negatives right there, so we could get propensity scores. So it's kind of interesting. You know, you're seeing here the limits of what these estimators can do. At least that one, you're not going to be able to get. So if you don't have a group of you know, a donor pool of units that are never treated, you're limited in what you can do with this estimator. But you can go all the way up there to the very end using those not yet treated. Okay. All right. So in conclusion, they also proposed this bootstrap procedure to conduct these asymptotically valid inference, which can adjust for autocorrelation, clustering. So in conclusion, chances are you're going to write more papers using diff and diff than any other design your whole life. It's just very common because the opportunities are there all the time. So in my opinion, there's basically 3 papers that are worth your time. Goodman-Baker 2018, Callaway-Santana 2019, and a paper I didn't get to cover called Sun and Abraham 2020. The Sun and Abraham one is about the event studies. And I'm going to show you before we're done a GitHub directory, a repo that will allow you to download code to properly do event studies that will get you those pre-trends. Again, it's just like Callaway and Santana. It's a weighted estimate of each of those coefficients that doesn't use the already treated as a control. Okay, and as a result of that, what it ends up doing is give you, once you do the proper weighting, exact parallel. You know, it looks like this. Let me show it to you. When you follow this Callaway Santana, this Sun and Abraham estimator, which actually is identical to the Callaway and Santana estimator on some parts of it. When you do it, that's not the one I wanted to show. I want to show you this one. Here is the two-way fixed effect one. Remember how it was declining? Here with Sun and Abraham, it ends up being exactly 0 off of this exact simulation, and then ends up identifying the full treatment path ex post. Okay, so I will post for you the code to do that in a little bit. Let me see what someone has said. The name of the third paper is called Estimating Dynamic Treatment Effects in Event Studies with Heterogeneous Treatment Effects. Again, what is this new diff and diff literature about? It's about heterogeneous treatment effects and the problems with OLS. And many of them are doing the same thing, which is dropping. Here, I can put, Andrea, let me put this in the GitHub. Oh, it's in there already. It's in there already, Andrea. So you can see here what we're doing. What can we do that's different from two-way fixed effects? Because two-way fixed effects is biased. Secondly, how do I handle heterogeneity? Each of them is really doing pretty similar things, which is like a weighted, it ends up being like a weighted regression. So I'll show you just sort of an example of what it's in section 4, what their alternative estimation method is. Look, it's just going to be a group specific. It's an ATT. They call it the cohort specific ATT for a bunch of leads and lags. Okay, summing them up just like this is exactly the same form as Callaway and Santana, but they're just doing a weighting over the size of G. Okay, so ends up being actually ends up working really well. So that I will show you before we're done. I will show you the code to do that, and then you can read the paper and read the code, and then you'll have the 3 canonical papers. Really, there's another one by Aaron Dubé and Zipperer and someone else that does something else. There's a couple of others. It's not the only ones. There's a French team that just got an AER, but point is, a lot of them are trying to figure out how to handle keeping those never treated out of the comparison groups. And they do so different ways, but they all kind of have like a similar unbiasedness, consistency property. And I guess that there's several ways to do it, but two-way fixed effects with those already treated in there is just not going to do it. Okay. All right. So, yeah. So that concludes the diff and diff material. What we're going to do now is we're going to do synthetic control, okay? We're going to do synthetic control, and we will then conclude, okay? Slides, synthetic control, right? We will conclude after that. Synthetic control has been called by Athey and Embens the most important innovation in causal inference in 15 years. It was developed by a man named Alberto Abadie in a 2003 American Economic Review, looking at the effect of terrorism on GDP in Spain. It was a terrorist attack that only hit the Basque country. And what he did was he developed an estimator that would, it was a very exotic type estimator. Remember, Abadie is the one that did that semi-parametric diff and diff paper that I just said was a companion to Callaway and Santana. It ended up doing, ended up identifying that effect when you only have one treatment group, okay? So it's extremely useful for what are called comparative case studies. And comparative case studies are situations where you have just one event that affected one unit. And that's nice because lots of times that's all we have. Lots of times all we have are case studies. So it continues to be methodologically a frontier for applied econometrics. I have yet to fully update my slides, nor did I update my mixtape revision for Yale to go into all of the new material. There's just a lot, and it's not really clear how it's all going to shake out, so I didn't do it. So I'm just going to go over the seminal Abadie, Diamond, and Hay-Mueller 2011 Journal of American Statistical Association paper, right? And this is just a starting point, and you'll build on it, on top of it later with your own work. So what is a comparative case study? It's a single treated unit. It's a country, it's a state, it's a firm, it's a school. It's just that it's one country, one state, one school, one firm that has been treated. There's two ways that social scientists have tried to study that. They either study it qualitatively or they study it quantitatively. And in political science, you'll see a very stark division between these two qualitative and quantitative camps, but you don't really see it in economics because we don't have a qualitative camp really at all. You know, there used to be more of qualitative research. Ronald Coase, in his theory of the firm, actually went around to a lot of managers and just asked them a lot of questions, and out of that came his theory of the firm work. But that's not really super common, okay? So qualitative comparative case studies, the goal is to reason more inductively. So you sort of like study something and then you kind of out of that have like a set of mechanisms and a set of causal chains that are really drawn more from logic and induction through historical analysis. It may not answer the causal questions at all because they'll rarely be a counterfactual, or if so, it's a completely just arbitrarily chosen one. Classic example of a comparative case study is Alexis de Tocqueville's Democracy in America, which started comparative political science. And he is using a comparative case study. Literally, he'll be constantly comparing America to France, right? But many of these studies don't do that. Versus a traditional quantitative comparative case study. Now, what is a traditional quantitative comparative case study? It's a comparative case study where there will be an explicit counterfactual. There'll usually be some natural experiment, though these will oftentimes be, large events, exogenous shocks, applied to a single aggregate unit, like a city, school, firm, state, country, and then you will just compare the evolution over time of that one treated unit with some weighted average of the other treated control group units. It's just that why you chose those control groups is kind of vague. Right? So the pros of the quantitative case study approach, the traditional one, is that we oftentimes have policy interventions that are taking place at an aggregate level. And we oftentimes have data at the aggregate level. So it's perfect, okay? But the cons or the negative parts of it is usually in those studies, we didn't have a way to pick our control groups that was principled, meaning that was like grounded in a unbiased, or not unbiased, but like an objective, impartial rule, all right? Selection of the control group was usually chosen by hand, right? You just said, oh, I think I'm going to pick these 5 countries. I'm going to pick this neighboring country. Think about the Carden-Kruger minimum wage study. What's the control group for New Jersey? Pennsylvania. Why? It's next door. Well, why does that matter? Why is it being next door mean it's going to have parallel trends? I don't know, right? So usually it's just not really well thought out, or not that it's not thought out, but it just kind of picks a unit. But the other thing is too, is that when we run regressions on those things, our regression-based standard errors are based on sampling variance, and that doesn't actually reflect the uncertainty about what's going on in a quantitative comparative case study, which is we don't know if the control group actually can reproduce the counterfactual of interest. So you've got inference issues, you got selection issues. So what I'm going to talk about is a paper by David Card called the Marial Boat Lift paper. It's not called the Marial Boat Lift paper, but it's like, it's got Marial Boat Lift in the title, and it's a study of the effect of a large immigration shock on domestic wages. Okay, so this is a picture of a group of Cuban individuals who were allowed to exit Cuba in 1980. Fidel Castro, the dictator of Cuba in 1980, gave permission to any resident of Cuba. If they wanted to leave, they had to leave from the Marial Boat Lift in this particular period of time. Marial Dock. They had to leave on a boat lift from the Marial Dock. Most of them went to Miami, okay, which is like the nearest city. So here's a picture of some happy people. Look, they're all very happy. Look at these people, they're smiling. Look at these people, they're smiling, right? So this is a very happy event. Huge exogenous shock, okay? It increased the Miami labor force by 7%. And Card wants to know, well, look, we have an exogenous shock to labor supply coming from, a huge number of immigrants. This is a classic question in labor. Do immigrants lower employment or increase unemployment amongst native workers, right? Does it change the wages? Does it change employment? Well, what he's going to do is he's going to get individual level data on unemployment. So he's going to look at unemployment. He's going to get individual level data on unemployment from the current population survey for Miami. He's going to use 4 comparison cities: Atlanta, Los Angeles, Houston, Tampa, St. Petersburg. Now you have to remember, it's 1990. He doesn't have synthetic control. Okay? He does not have synthetic control. So he's going to use his own best judgment. Here was his best judgment. Tables 3 and 4 present simple averages of wage rates and unemployment rates for whites, blacks, Cubans, and other Hispanics in the Miami labor market between 1979 and 1985. So we have a before and after. It's actually a G-1. Look at that. It's like a T, and it's an average treatment on the treated for the, for Miami in 1985, and then using 1979, G-1 is the pre-treatment. For comparative purposes, I have assembled similar data for whites, blacks, and Hispanics in 4 other cities: Atlanta, Los Angeles, Houston, Tampa, St. Petersburg. Why did he pick those? Here's what he said. These 4 cities were selected both because they had relatively large populations of blacks and Hispanics, because they exhibited a pattern of economic growth similar to that of Miami over the late 70s and early 80s. A comparison of employment growth rates based on establishment level data suggests that economic conditions were very similar in Miami and the average of the 4 comparison cities between 76 and 84. If you are just arbitrarily picking a group of cities, characteristically of David Card, it is quite principled. He's looking through, he's trying to find units that are pretty similar to Miami on those factors that are strong predictors of employment and wages: population, economic growth, right? That's what he does. But there could have been lots of cities that fit that, right? So here's Card's main results for unemployment. And look what he finds. He finds no effect on unemployment using the diff and diff. He finds nothing for whites, finds nothing for blacks. Now, the standard errors are huge. So you've got these confidence intervals, but that are pretty large, but the point estimates are negative, not positive. So Card found that the Miami boat lift reduced unemployment compared to the 4 cities he chose. Is there anything principled that we could do that doesn't give the researcher so much control over the control group? And that is where synthetic control was developed. Baudier and Gardezabal, 2003. I think Baudier may have been a Josh Angers student at MIT. I'm not positive, but I want to say that he is. He's now at MIT. Baudier and Gardezabal, 2003. Baudier, Diamond, and Heymüller, 2010. All right, so the first one appears in Baudier and Gardezabal, 2003, in a study of terrorist attack in Spain, one region, Basque, compared to a weighted average of the rest of Spain. All right, looks at the effect on GDP. Gets revisited again in 2011. More proofs, more stuff about inference. All right, 2 political scientists are the co-authors. And what he basically is arguing in this is when you use a comparison group that is a combination of comparison units, it will often do a better job reproducing the characteristics of the treatment unit than if you had just used one single comparison unit. Okay, so our goal here is to reproduce, this is your objective. Your goal is to reproduce the counterfactual for a treatment unit by finding the combination of control group units, the untreated units, that best resemble your treatment unit prior to the intervention in terms of covariates. These covariates need to be predictors of the outcome of interest, because once you get a group of units, that once you have balance on those covariates between the treatment group and the control group, you're then going to use them to build the counterfactual, because the counterfactual, called the synthetic control, is going to be a weighted average where the weights came from that initial first step that I just described. The method is going to calculate a counterfactual, an estimated counterfactual, that's the weighted average of all potential comparison units that resemble the characteristics of the treatment unit in the pre-treatment period. That's the synthetic control. All right, so let me tell you a little bit about this estimator. It's an alternative to regression. It's funny, when I first started developing causal inference, I just thought it was all going to be about regression. Here we have another design that is not a regression. We saw that in diff and diff. We have some problem with regression. Saw it with synthetic control. Problem with doesn't going to use regression. Regression discontinuity, various kinds of kernel regressions and non-parametric estimators, and IV, we did 2-stage least squares, which is regression, but sometimes we need to use Lemel or jive, right? So we got these, like, it's kind of interesting that regression as your single bullet in your gun is probably misguided. We want to have actually more bullets in the gun that can do more things, because regression, no matter how great it is, doesn't handle certain things super well. Right, so the advantages are regression will extrapolate beyond the support of the data. If you remember, with regression discontinuity, that was why we liked regression, was because it was extrapolating beyond the support of the data. Right, that's not what synthetic control is going to do. Synthetic control is going to only have as a control group a group of units that that form a geometric shape called the convex hull. And the convex hull is something that will contain the treatment group value in the pre-treatment period. Right? So there is no extrapolation. Our estimates will always be a comparison between a treatment group and a set of control group units, a weighted average of a set of control group units, as opposed to projecting out, beyond of any support of the data as we do with OLS. Doesn't require access to post-treatment outcomes in the design phase of the study. You don't have to be looking and peeking at the results when you're estimating your model. Makes explicit the contribution of each comparison unit to the counterfactual, and it's going to formalize the way comparison units are chosen, which is going to have direct implications for inference. It has disadvantages too. So it's funny, like what I said over here. Is there anything principled we could do that doesn't give the researcher so much control over the control group, right? That was the selling point of synthetic control. And I think that's a little overstated. It's not that you are picking your controls directly. What you are doing is you are picking the covariates that you will use for your matching. And as a result of that, you get to indirectly pick your synthetic control because you are picking the model. So what that does is the researcher bias isn't in the selection of the control group units, it's in the model selection, model specification stage. And there is significant diversity at the moment as to how to principally select models. People have suggested machine learning. They have suggested various modifications to the estimator altogether, as well as different estimation methods in different software. Furman and Pinto have a paper in the Journal of Policy and Management, and they recommend showing a few different results. Show your results using a few conventional strategies for picking your covariates. And once you do that, show you how robust your results are to a few of those specifications. All right, so here's the estimation. Here's the notation. We're going to have J+1 units. So in the United States, we have 50 states and District of Columbia, which gives us 51 state units over some stretch of time. Unit 1 will be the treatment unit, and that will leave us with J donor pool units. Right? It's a reservoir of potential controls, and interestingly enough, these are never treated units. They're never treated over the panel. You have to drop all the treated units over the panel, so it's got to be a true untainted donor pool. Got potential outcomes notation because we can do everything with potential outcomes notation. Y0 is going to be the outcome, potential outcome for the unit I at time t in a world without the treatment. And Y1 is going to be the potential outcome that would be observed for unit I at time t if unit I was exposed to the intervention in periods in the post-treatment period, right? So we got Y0, we got Y1. The treatment parameter is going to be Y1 minus Y0 at any particular period of time in the post-treatment period. And by the switching equation, the treatment group unit Y1 is by definition Y, so we just have to compare Y1 to some hypothetical counterfactual state of the world Y0. Right? So we're going to be estimating that. And by estimating that, we just take simple differences. It's really straightforward. So what are we doing when I say we're estimating Y0? What exactly am I doing? What I'm actually doing is I'm estimating a vector of weights. These weights will be applied to all of the control group units. So when they are applied to the control group units, it is a linear combination of every unit weighted by these optimally chosen weights, which will then give you the counterfactual for your treatment group, okay? So it's going to be a vector of W, control group unit 2 all the way to J+1, where Wj is going to be non-negative, so the weights have to be non-negative, and they must sum to 1, okay? They have to be non-negative, they must sum to 1. And each value of W is going to represent a potential synthetic control. You're going to match on X. X is going to be a vector of pre-intervention characteristics for the treatment unit, and X0 is going to be a stacked matrix of that one particular variable across all the units, okay? All the control group units. And you're going to be basically minimizing the distance between X1 and a weight applied to X0, okay? This is going to be your norm that you're minimizing. X1 minus X0W. The solution to this is going to give you, there's a unique solution to this subject to these weight constraints, and that's going to give you the vector W star, which will be a set of weights that minimizes this expression subject to weights being non-negative and weights summing to 1. Okay, so we've got here optimal weights differing by a weighting matrix, another weighting matrix, which is V. So we have this norm, which breaks out into this matrix expression right here. Okay, we've got X1 minus X0W prime times V times X1 minus X0W. Okay, so what is this V? V is a K by K symmetric and positive semi-definite matrix, right? And it can have anything inside it. It's just got to be symmetric and positive semi-definite, all right? So the reason why it matters is because when you are minimizing this expression, the V's right here, okay, so now we're getting into this actual, row by row summation notation. This V is modifying these X's. Okay, so if you're choosing W's that minimize this entire expression, okay, then the V's associated with particular covariates are going to change those W's. So let's say that your X, let's say the one X you had was population, okay? Let's say you had two, actually. Population and GDP, all right? And you want to really weight GDP more than you want to weight population. Let's say you want GDP to be a 0.9 and you want population to be a 0.1. Well, that means that the optimal W that's going to minimize this expression is going to pay more attention to population GDP than it is to population. So the optimal vector of weights that you get for that V will differ than if it was the other way around, if it was 0.9 for population and 0.1 for GDP. So all that V is a weight that reflects the relative importance that we're going to assign to the nth variable, right? When we measure the discrepancy between the treatment group and the control group units. So what should it be? Well, think about what we're doing. What are we doing? We are trying to get weights that will reproduce the behavior of the outcome for the treatment unit in the absence of the treatment, which is the pre-treatment period. So why don't we choose V that has that characteristic that emphasizes those covariates that helps minimize the gap in the pre-treatment period, right? So it's very common to simply let Stata use an optimal set of V star rather than loading it in and ad hoc choosing it. Allow it to be that you will minimize two, you'll have two unknowns with two constraints, W star and V star, subject to the summation of W equaling 1 and W being non-negative, okay? So what you could do is just allow V to be the solution to V that minimizes the prediction error in the pre-treatment period, okay? And that's what we're going to think about. All right. So I'm just going to give you a little bit of insight into the estimator and how it works. So we've got this Y0. It has to do with a factor model, okay? Factor models are similar to these panel regressions. You've got heterogeneity modeled that's kind of changing over time right here, this modeled heterogeneity. And you've got these, they call them common factors, factor loading. So you've got alpha T, unknown common factor with constant factor loading across units. Lambda T is a vector of unobserved common factors. Okay, so that's our equation. What we're going to do is we're going to subtract from this, from the left, the synthetic control, and then to the right, what we're going to do is we're going to subtract from the right what that synthetic control equals when it's expressed in terms of these four terms, right? So we're going to say y0 minus that synthetic control. Ultimately, this right here is going to be a weighted average over alpha t, so it's going to eliminate. And what you're going to end up getting is W star lambda, lambda prime lambda inverse lambda prime epsilon minus W star epsilon minus epsilon. So this is the treatment group unit. This is the donor pool. This is the treatment group unit. This is the donor pool. You need these to be zero, right? If these are zero, then there's no difference between our treatment group in the control group period and our control group units in the control group period. So if lambda prime lambda is non-singular, then the right-hand side will be close to zero, right? If that's non-singular, then the right-hand side, all of this will be close to zero if the number of pre-intervention periods is large relative to the size of the transitory shocks. So here's our transitory shocks here and here. And if it's very large, then the average over that epsilon, so long as it's a good fit, will be this will be approximately equal to zero. And the idea of why synthetic control works is that if these are zero and these are zero, then this right here is equal, this y0 is equal to the donor pool, the average donor pool. Only units that are alike on observables and unobservables should have the same patterns over time, over long stretches of time. All right, so when we get back, let's take a break now. Let's get back at 7. When we get back, we will finish up synthetic control. We will do a replication. All right, so let's come back in just a moment. We will do we'll come back at 7 o'clock and we will spend the next hour on synthetic control.